Hello everyone to the lecture today, which is a little bit different than the lectures we had during the semester. I want to get back to this idea of having an online lecture again. What we're going to do is we now finished the part where all the system dynamics, and we talked a lot about PID control, root locus design, and went through all the add-ons. So it's actually time now to finish up with our Airbus A300 control design. So a little bit of background. This actually was a lab exercising during COVID. So you were supposed to do that at home when you were a student during Corona, and then discuss it with me online or send it to me online, right? Now we are back to the regular lab where we have different experiments, which are more like actually working on a computer with a professor in the lab. But still, this A300 is a nice example because it gets you through all the system dynamics part and then designs a controller. So I thought this actually is a good idea to get that whole A300 example on video and have it in our Moodle course. Okay. And last but not least, it actually summarizes all what we have done so far, namely system dynamics and a control design, which I'm going to do on the root locus, and also going to show you some Matlab, right? So that's the plan for the next, I would say, hour. For those who are actually regular in the class, I will also read you the A300 analysis of the aircraft model, right? So you might be able to go a little bit forward in the video. But as we do not have both experiments on video, so I'm going to start actually with the analysis of the model. So I'm going to do the calculations with my pad. I'm going to discuss the problems, and then I'm going to show you some Matlab. And for the control design part, there's a little bit of a Matlab exercise involved anyway. I think it's a nice idea to actually show you how controllers are designed in practice when you have an actual model using a computer-aided tool. In our case, it's going to be Matlab. Okay, so that's the plan. Hope you enjoyed. And I'm going to switch over now to the actual problem, and I'm going to introduce it, then we'll do a little bit of a discussion, and then we start it right away. Okay, so when you go on our Moodle course, you will find during the exercises, no, it's not under experiments, it's under exercises, you will find the analysis of the A300 aircraft as well as the control design. Okay, so this first part will analyze the A300 aircraft model. Okay, so we're going to take a look on transfer functions, calculate poles and zeros, mathematical operations in Laplace domain. We also take a look at the initial and final value theorem, and we then going to do some, finally we're going to end up with drawing some block diagrams. Okay, some general introduction. So the A300 had originally an analog flight control system, right? So very basic, and it was digitalized in the early 80s to a full digital, obviously, flight control system. And we're going to actually design a very small part of it. And we are dealing with the pitch dynamics. So for those who are hearing flight dynamics this semester, or even flight controls, they should be quite familiar with that. In the pitch dynamics, we have the so-called the flight path angle gamma, we have the angle of attack alpha, we have our pitch rate Q, and we have the attitude, the flight attitude theta. Okay. In our case, we're only going to consider one single flight point in the whole flight envelope, right? So what that means, obviously the dynamics of such an aircraft do change when you change the speed, when you change the altitude. For us, we're going to pick a single flight point. It's a cruise flight point of the A300 at 10,000 meters altitude at the speed of 264 meters per second. And what we have is an ordinary differential equation of describing on how the elevator deflection here actually acts on our pitch rate, right? And we're going to do some analysis using that ODE, and we're going to work a little bit just to get some idea. Some comments on what you would actually do in practice. Yes, you would actually design a flight controller in that way. However, you would have multiple points in your flight envelope, right? So you have to do this a couple of 100 times for different flight altitudes, for different speeds. But the idea, how you do it, is basically always the same, right? Okay, so let's start with analyzing our system. The first question being asked is, name the behavior of the system above based on the ODE. So what system behavior do we have? Well, if we take a closer look here, I'm going to switch to drawing, let's change a nice color, probably that one. Well, we have here the second derivative of Q. That means we have a second order lag. We also have a proportional part where our input goes in, so it's definitely going to be proportional. But we also have the first derivative of our input, so we have a PDT2 system. Okay, first problem solved. First points in at the exam. Okay, so to further analyze the system behavior, we want to actually compute the transfer function from our elevator deflection to our pitch rate. So this is exactly what we have here. So we just do a simple Laplace transformation to get the transfer function of our plant, which is from the elevator deflection to our pitch attitude. Well, if you do that transformation here, you simply go, the second derivative here is s squared, so you're going to be ending up s squared plus 1.8s plus 3.27 in the denominator, and in the numerator you go 3.6s plus 2.52. Okay. That's already what we have for our transfer function. So now determine our poles and zeros. Well, we need, for the zeros, we need to set our numerator to 0. Okay, so mu equals nothing but minus 2.52 over 3.6, right? So if you set this guy here to 0 and bring it on the other side, so your 0 is located at minus 0.7. So we do have a left half plane 0, which is actually quite nice. So we don't have the problem of right half plane zeros, which we would have if this guy would have a positive real value, but it's negative, so we're fine. Okay, for the poles, we have to set the denominator to 0. So we solve the midnight formula for the poles. So our two poles are located at minus 1.8 plus minus square root of 1.8 squared minus 1 times 3.27, and that whole thing is divided by simply 2. If you solve that, you're ending up with minus 0.9 plus minus roughly 1.6i. Okay, so what can we tell already here? Our system is stable, right? So we have a negative real part. The real part is smaller than 0, so it's going to be a stable motion here. So the aircraft is stable, and it's going to be oscillating because we have an imaginary part here, right? So the imaginary part is not equal 0, so we will encounter some oscillations. Sorry. Okay. Well, that's actually what the next question is. So it's stable because of the right half of the real part being negative. And now we can actually compute the eigenfrequency and the damping. Well, if we take a look, I can actually write it down. So we have s squared plus 1.86s plus 3.27 in the denominator, and this we can do comparing the coefficients with 2d omega 0s plus omega 0 squared. So it follows that we have omega 0 nothing but the square root of 3.27, which equals yeah, good question what it equals. Let's do the calculator quickly. 3.27, and we're going to do the root, so we have 1.8 radians per second. And for the damping, we have 2d omega 0 equals 1.8, and if we solve that, it follows that you see that omega 0 is 1.8 this here, so that actually becomes equal 1. So if we divide it by 2, it follows that we have a damping of 0.5. So we actually do have some oscillations with some overshoot there, right? Okay, so next question. Beside the pitch rate, the pitch angle or flight attitude is also of interest. The connection between, which we know from flight mechanics, is that the pitch angle theta is simply the integral of the pitch rate. So, and now we should determine the transfer function from the elevator deflection eta to the pitch angle theta. Well, what should be, or what the idea behind is that if we want to integrate in the Laplace domain, this is simply multiplying by 1 over s. So you can simply, and this is the very big advantage of the Laplace domain, you can simply take that transfer function here and multiply it. Oh, actually, there's an error here, which I did not see. I'm quite sorry about this one here. This needs to go theta q, right? So we are asked for the pitch rate q. But if we want to know how actually we get to the transfer function from our elevator deflection to not q but theta, we simply need to integrate this transfer function, right? So we know that the transfer function from eta to our pitch angle is nothing but taking the transfer function from the elevator to our pitch rate and integrating it, which is nothing but multiplying by 1 over s, and that's actually already it. So, and if we take a look how that transfer function looks like, it's 3.6 s plus 2.52 over, we got the 1 over s, and then we have this quadratic polynomial s squared plus 1.8s plus 3.27, and this is now our transfer function from the elevator deflection to the pitch angle, where we see it has an additional integrator in there, obviously because we integrated the transfer function. Okay, so the next thing now is we should draw a pole zero map for that transfer function here, right? So for this guy, please note that we should do it for the transfer function from the elevator to the pitch angle, not the pitch rate. So we need to encounter that s as well here, which is a pole at 0. Okay, so let's try to do that. Okay, so our poles were actually at minus 1.8, which is, so we can actually select the scaling here. So we're going to say minus 1, minus 2, and we're going to select 1, 2, minus 1, minus 2. We don't need the positive side because we all have negative real value, so that's okay. So our 0 was at minus 0.7, which is here. We have here an additional pole at equals 0 because we added the integrator, right? This guy here. So we can plug it in directly. And let's check the poles one more time. They were at 0.9 plus 1.6 I, so 0.9 would be here, 1.6 would be 246 would be here, and obviously we have it symmetric, so here. Okay, so we have 3 poles, and we have then 1, 0. So far, so good. Okay, next we want to check the time response of the pitch rate Q. For a realistic input signal, we are going to assume that the pilot is putting in 5 degrees of elevator deflection constantly, meaning that we have a step input of with an amplitude of 5. And now we want to know the initial and final value of the time response Q directly from the transfer function. Okay, so our transfer function, let's write it down one more time. G of S was nothing but, I'm going to cheat a little bit, it was 3.6 S plus 2.52 over S squared plus 1.8 S plus 3.27. Okay, so now we want to do initial and final value, so you know you have to apply the initial and final value theorem. So let's go with the initial value, where we need to set S equal to infinity. And now you should remember when you think about, okay, let's actually do it nicely. So the initial value is limes of S going to infinity of the transfer function here, 3.6 S plus 2.52 over S squared plus 1.8 S plus 3.27 multiplied by S, and we need to multiply, don't forget that, by the input. The input is a step with a value of 5, so it's 5 over S. We immediately can cancel here, and now the trick, when we let S go to infinity, we need to actually divide every term here by the highest power of S, which would be S squared, and then these terms would all go to 0, and your initial value would get 0, okay? Not that surprisingly, because we are dealing with an actual physical system. And we said for physical systems, it is always the fact that we don't have a feed-through, that's what we call it. We have an initial value of 0. That means an initial value not being 0 means whenever you apply an input, it immediately shows up at the output, and physically this is not possible, right? Okay, so more interesting might be the final value of that input of the pilot here. Well, we basically have the same thing as above. The only difference is we do set S going to 0. The rest remains the same. And what we get is basically 5 times 2.52 over 3.27, which is nothing but 3.85. Meaning that if the pilot commands an input of 5 degrees at the elevator, we are getting a value of 3.85, and this would be actually degrees per second here, right? The unit, the speed, the pitching speed. Okay, use either the result from the last point or the transfer function directly to determine the static gain K0 and the high frequency gain K infinity. Okay, well, for that transfer function, if we have this initial value being 0, obviously our high frequency gain, where S equals goes to infinity, also needs to be 0. And the static gain here, case 0, is nothing but if you would do the final value with an input or a step input of 1, right? So your case 0 of that transfer function is you get by setting s to 0. So it's 2.52 over 3.27 equaling 0.7. So the connection between the static gain and this guy here is, well, just a multiplication of 5, because we have an input of 5 degree, right? Because we don't have an input with an amplitude of 1, but with 5. So we need to take the static gain here multiplied by 5. Okay, so far so good. So we go to the next question. And now we are actually at the point where we want to draw some block diagrams. So in the second part of the exercise, we actually want to design a pitch rate controller, which is actually a standard control element in each flight control system what you have in today's aircraft. To prepare for that, we want to draw the block diagram for our transfer function and include the error and name everything right. And this is actually a pretty often asked question during the exam, right? So to be able to draw a block diagram of a closed loop. Okay, so we have our transfer function where we have the elevator deflection going to our pitch rate. The output obviously is our pitch rate here, and we have an error. We have a controller which takes the error and proceeds it and gives us the elevator command. So here would be our elevator command. We would have a reference signal. That reference signal would be any pitch rate the pilot wants to command. And then we have that feedback signal here. We're constructing the control error E, which is nothing but our commanded pitch rate minus our actual pitch rate. And now we got everything for that exercise. Finally, we should calculate the closed loop transfer function, the complementary sensitivity from our reference Q command. So our output Q is nothing but our complementary sensitivity, which is R of S times G of S over 1 plus R of S times G of S times our commanded pitch rate. So this would be the transfer function going from here, from our reference, to the output Q here. And that's already it for that first part. I actually want to show you some more results now in Matlab, because now we just did the initial value, the final value of a step, but we obviously can also look at the actual dynamic behavior. What are the poles doing? We figured there needs to be some oscillations in there, and this will give us further knowledge about the control design later on. So I'm going to switch over back to Matlab, where I've implemented this, and this is actually also something. Okay, now my camera is stuck, but yeah, that's a usual problem. Now it's working again. So that's also actually on the Moodle servers. You can simply download that file and see also the results of that aircraft. Okay, first of all, here's the inclusion of the let's zoom in a little bit of the system. And what's more interesting, we're actually computing the damping in the eigenfrequency. And here are the poles, what we actually also got out of our analysis. We got the damping. So it's not totally exactly 0.5 because there's some small difference in that implementation here, but we got close enough. And here's our transfer function, right? So again, if you take a look at the pole zero map, this is the pole zero map now only for the transfer function from the elevator angle to the pitch rate, so it has only these two poles and this 1, 0. If you would plot the transfer function for the elevator command to your pitch angle, you would still you could actually simply integrate this guy here. Actually, I can do that in a second, but I want to show you the step response first. You can call the step response for our aircraft system simply by step, and it gives you this answer. So we are going for a step of 1. We are getting to this final value, which is actually close to our steady state, or it's actually our steady state gain, which was 0.77. So here, what you see here, and we see that huge overshoot here, which is if you compare it with your actually damping, it's a little bit more you encounter here. This is because also the 0 plays a role in this response. Okay, so actually we could call Matlab for a second, just to show you that I'm not actually telling any rubbish. Well, so I already did that before. So we have our transfer function, which is the transfer function from the elevator command to our pitch rate. So for example, you could do simply call a step here, and it will give you this answer what we just saw. Yeah, whenever a recording runs, Matlab is actually pretty damn slow because the OBS system takes up a lot of CPU power, so we have to wait. But now it appeared, right? So this is actually what I just showed you in this Matlab live script. Okay, so far so good. And now we would say we are interested also not only in pitch speed, but also in the pitch angle. So we said by just doing an integration. So we could say, let's call that G2. We take our transfer function and we do an integration. So we multiply it by 1 over s. So we divide, it's the same as dividing it by s. And now Matlab immediately gives us our transfer function. It looks a little bit different because Matlab directly multiplies that s in the denominator, but you could, for example, say pole 0 gain of this G2, and Matlab converts it then to the 0 pole gain to the pole 0 form. And now you see it looks a little bit closer what we have. We have this explicit second order polynomial here. We have this explicit s with the pole at 0. We have our 0 here, and we have this remaining element of 3.6. Anyway, what I wanted to show you is now that we are also could take a look at the pole 0 map here. If we do so, we should actually encounter something which looks similar to what we have in our what we actually have drawn in our exercise in the PDF file. Well, you see here are the poles. Here is the 0. Here is the pole at 0. So it's not that nicely visible. So we can do some tricks here. We could, for example, say x is equal, and then we should get a better view here. And now you immediately see that you have the poles, which are at minus 0.9 plus minus 1.6, and we have this integrator pole here, and we have this here. Okay, so all what you are, and this is an important thing, whatever you have actually in your files, you can also do in Matlab pretty easily. There's only a limited set of commands we need for that, but actually the Moodle course provides you all of this if you want to go a little bit deeper into controls and code the stuff yourself. Okay, talking of which, we are actually can head over now to this second exercise where we actually gonna do the control design. So I'm going to switch over again to our PDF file. Okay, so in the second lab exercise, we are actually want to design now this controller for our aircraft, for our pitch dynamics. We're taking the very same pitch dynamics we had before. We're going to do first the design of the root locus on paper. So we're going to draw a root locus plot for our system here. Then we gonna learn how to use Matlab to give us a root locus plot pretty quickly. We're going to close the loop in Matlab and analyze this closed loop. We're going to add some dynamics to the controller to achieve certain design specification. And we're also going to do pre-filter design, what we actually learned about in last week's lecture, right? So it's a lot of stuff in there, and I hope you kind of find it interesting. So the introduction I can skip. However, we're shortly going to talk about the design goals here. Well, we saw that our transfer function had a damping of 0.5. This is suboptimal, right? So we want to increase the damping to 0.7 because it will have less overshoot. And we want to make sure that there is no steady state error. So if the pilot actually commands a pitch rate which he likes to have at the output of the aircraft, or to have that the pilot likes that the aircraft actually achieves, the aircraft should also achieve that, right? So we want to make sure that we have steady state accuracy. Should ring a bell thinking about integrators in the controller and stuff. But we are not there yet, so let's go step by step. Okay, here's a recap what we just had, the dynamics, our transfer function, which were now analyzed. We have an Eigen frequency of 1.8, which, and the damping of 0.5. One small note here, if you're also listening to flight controls, you may figure that if you go through the regular coordinate systems of flight mechanics, you will figure you actually need positive feedback because to actually stabilize or generating a pitch down command here for an aircraft, you actually need a negative deflection of the elevator, and this is actually, you have an explicit sign change which I'm not going to consider here. So for this part, I put in another sign change, so to say, so that we can work with a negative feedback, right? But just be aware of that if you design an actual controller in practice, or if you're in flight controls, there might be a different sign here which you explicitly need to consider. Nothing serious, right? So, but it's just it would be a little bit of a distraction here, so just change the sign for our convenience. Okay, so the first thing what we need to do is, to be able to perform a root locus controller design, we have to recap the poles and zeros of our system, which are at minus 0.9 plus minus 1.6 J. So we're going to plug them in here. Remember, we are actually drawing them for the open loop system, and then the root locus gives us the location of where those guys are, which points are achievable in the closed loop. So, okay, with that scaling here, we can draw the 0 in here, and we have the poles at minus 0.9 plus minus 1.6, which is here, and we go symmetric here. Okay, so far so good. We have the poles in there, we've got the zeros in there. Okay, so let's scroll down. A damping ratio of 0.5 is too low, so we want to increase that to understand. We basically want to understand, can we increase the damping for that system without including any dynamics, right? And for that we need to draw the root locus curve. Okay, so we should draw a text marker and draw in our plot which part of the x-axis actually belongs to the root locus curve. So instead of a text marker, I'm going to use something here. Yeah. Okay, this is rule number 5 of the root locus design. Whenever you look to the right, you should see, encounter an odd number, and then the x-axis belongs to the root locus curve. So here, this part does not belong to the root locus curve because it's 0. As soon as you cross over to here, you're actually have one element. Then you get to the point where you have these 2 poles. Adding an even number to an odd number always gives you again an odd number, so that you don't have any change here, and this whole part needs to belong to our root locus curve. Okay, so far so good. First question done. I'm going to go back here. Okay, calculate how many how many curves do we need to following rule number 1. Well, it's the maximum number of poles and zeros. We say we have a physical system. We only need to count the poles, which are here too. So we're going to have 2 curves. Rule number 1, how many curves go to infinity? Well, subtracting the number of poles from the number of zeros. So it's going to be 2 minus 1, meaning that 1 curve needs to go to infinity. Okay, so determine the centroid location and as well as the angle of the asymptotes. Well, for the centroid location, we need to add all the real parts together. So we have 0.9 minus 0.9. We've got that twice, right? Because we have 2 poles at that location. And then we need to subtract the real parts of the zeros, which is minus 0.7, which becomes a plus. And then we divide over by the number of poles minus the number of zeros. And this gives us minus 1.1. So this is our centroid location. And for the angle, we only have 1, so our k equals 0, meaning that our angle immediately becomes 180 degrees. Or you could also say 180 degrees. Okay. With the gathered knowledge, you should be able to roughly sketch out the root locus curve. Remember, the root locus curves enter the x-axis at plus minus 90 degrees. Assume for simplicity the pitch rate feedback is a pure velocity feedback. Okay, that means we actually get a pure increase in damping. Okay, so what do we have? We have the centroid at 1.1, so let's draw that in there, and we know that this whole thing is part of the root locus curve. And also the asymptote. So if I draw the asymptotes from here in red, this is the asymptotes, this one asymptote, and it has an angle of 180 degrees, right? So it needs to go to the left. Well, if this whole part needs to be part of the root locus curve, obviously these guys here need to come down. And if we assume we have a pure velocity feedback, then this come down roughly in a circle. Well, this is not roughly a circle. So something like this around the origin, and this goes up here. So we enter with 90 degrees, and then 1 goes to the left and 1 goes to infinity, meaning 1 pole will end up in the 0 here, and as we figured, the other pole needs to go to infinity, and thereby we actually have sketched out the root locus curve perfectly fine. Okay, so far so good. But we should discuss that probably. So that means with proportional feedback, we can increase the damping here. If we assume the pitch rate is pure velocity measurement, that would be a pure increase in damping, but actually the pitch rate is not a pure velocity feedback. It also, it's a little bit coupled. So that means what we will see that a little bit later when we do the exact Matlab plot, we'll see that we also increase or change basically also the eigenfrequency a little bit. However, we actually, for the damping increase, and this is the main point here, for the damping increase from 0.5 to 0.7, we do not need any additional elements in the controller because we already can increase the damping by just the proportional feedback as the root locus curve goes to the left and down. Okay, so that's actually pretty nice. Okay, at this point you should understand how the root locus curve for the system looks like. You should also realize that damping increase is possible. Instead of computing the necessary gain on paper, we will do that this time in Matlab, right? So we're not going to solve the angle criterion. We have done that a couple of times now. So yeah, shouldn't be a big hazard. Should not be a big hazard. So we're going to do the whole thing in Matlab, and I'm going to try to hop over here to Matlab and see if we can get this done. Okay, so let's do this step by step. I hope this is now both nicely visible on your screen. Unfortunately, I cannot increase the size of the command window, zoom in there quickly, so we gotta live with that. Okay, first we need to define our transfer function. Use the command S. Okay, what I'm gonna do is I'm gonna clear my whole workspace so that you see I'm actually working fair. At this point, Matlab does not know what S, the Laplace variable, is, right? So we're gonna define that, and we're gonna use that transfer function command here, and we're simply going to define this S as the Laplace variable. Okay, and now we can put in our transfer function as we are set to do so. So we simply put in what we have here, right, and press enter, and now we have defined in our workspace the transfer function of our aircraft. Okay, so now we want to check if we actually have drawn our root locus curve nicely and on paper, and this can be done by simply calling root locus, and then Matlab is given the system. Again, it takes a couple of seconds longer because of the video, and then we get our root locus curve, and we actually see that we did pretty well compared what Matlab gives us. What I'm gonna do is I'm gonna again call x is equal, so it basically sets the x and the x and y axis to the equal size, and then I'm gonna do grid on. So with grid on, Matlab will show us the root locus grid, and now we see something interesting here. We see if the pitch rate would be a pure velocity signal, right, we would have a pure damping increase, so going here down along circles, but you see we are actually increasing the eigenfrequency with this feedback also, right? This would be the interpretation. If we click on that point, the open loop has a damping of 0.5, an eigenfrequency of 1.8. However, we are moving to the left, we're moving down not along a circle like these dotted lines here, which are lines for constant eigenfrequency, but we are also going to go a little bit, we are actually going to increase the eigenfrequency while we increase the damping, okay? Yeah, so much for the interpretation. In case we get stuck, call Matlab help. Well, if you need some help, but you can always ask Matlab to help you, right? Help root locus, and Matlab gives you a full document, actually the help on what you actually can do with that function. You can also call it for different system and so on. If you're not satisfied with that, you can also call doc locus, and then the whole Matlab functionality opens, and it gives you the whole documentation and also links to others. So you see that's actually quite a lot of stuff in there, which can help you. And to be fair, I'm actually using that Matlab documentation pretty often because I also don't know everything by heart. Okay. Okay, so far so good. let's switch back and let's see what comes next. So now we have the root locus. We're still in the open loop, but at the end of the day, we actually want to design the controller, right? So in case your root locus looks a lot different, then go back to Matlab, okay? It looks fine, so we're done with that. Matlab offers a pretty nice possibility to design controllers which are single input, single output. Single input, single output means that you actually have a system which has a single input and a single output, right? So this is called in English CISO system. It's it's a term pretty often used in control engineering. What would be in the counterpart of CISO would be MIMO, right? If you would have multiple inputs, multiple outputs. So for example, you have two inputs, U1, U2, and you have two outputs, Y1, Y2, right? So that would be MIMO. So whenever you heard that term, you know what it means. But for CISO, actually, Matlab provides pretty nice capabilities, namely a guided user interface, a GUI, which you simply can call via CISO tools. Right, and I'm going to do that. It's an interactive tool to design single input, single output controllers, and actually has a lot of plots in there which you might be interested, namely step responses, Bode diagrams, which we're going to tackle next week, but also root locus curves, and the root locus curve are interactive, and that is actually quite nice because you simply can drag poles around, you can add zeros in your controller and so on, okay? So, but I will show you that in a second. I'm just going to read through what I've written here. We also step response, okay, the damping, remember those lines, actually. So we can get the proportional control. Okay, so the idea here is we should actually find out how we get the proportional gain out to increase our damping to 0.7 and then write the controller down. Okay, so far so good. Gonna get that on the other side here, and then we're gonna simply do CISO tool, I think it's with S, and then it's G. Okay, it's not with S, it's without S, so simply call CISO tools G. So Matlab is smarter than me, it's proposing me the right function here. Okay, takes a second. In the meanwhile, while Matlab opens it, I can actually rescale here. Okay, starts opening. See, it's still busy here. So yeah, if you do it, it should be a lot faster because you're not filming and having OBS employed. So yeah, okay, now we're getting there. So what you see now here is, and actually I'm going to make that whole thing a little bit bigger, is the following. On the left side, you have the so-called Bode plots, right? They are in the frequency domain. We're going to start discussing those things in the next week. So we are not going to bother about those two guys here on the left. What we're going to bother about is this root locus curve and the step response. And now you're going to see that the thing is interactive because this here, you can grab simply the poles and shift them around, for example, to here, and Matlab immediately changes the step response, right? So wherever you put the poles, you will get the step response. Okay. If you grab them, you should take a look on the bottom here because it also updates in real time the damping you have in the closed loop. So I'm going to grab it again, and now we see we have a damping of 0.9. So we make the damping a little bit smaller. We want to achieve 0.7. again a little bit smaller. We're 0.8, so we're going to go further. I overshot because of the lag here. So 0.7, come on. Okay, let's go with 0.71. So it's a roughly, okay. So Matlab adapted our step response. Okay, we still have some quite overshoot, although we have a damping of 0.7, but that is due to this 0 we have in the numerator. Okay, but we know that the damping is actually the eigendynamics are well damped. Okay, we know we can do something smarter for to work with the 0, like a feed-forward controller, but we'll get to that. Okay, the question is now, where's the gain, right? So how do we find our control again? And this is what you find here on the left. If you would click here on the structure, Matlab would open the block and shows you what block means which structure here. We have our system G. We don't have anything for a sensor here. This is just one. And if we modify our controller, it's this block C here. Here, this F, what you see on the left, this would be a pre-filter. We're going to use that later. If you don't like that structure and you like working more with a feed-forward controller, you can change the structure, and Matlab will immediately update the values. But we're going to stay with this first selection. Yeah, you can make more complex. You can go with cascaded control, whatever you like. So it actually has quite some capabilities here. Okay, we're going to stick with that, and we know we need to see how our controller C looks like, and then we should know the value. Okay. So actually I should have, yeah, okay. So you simply double click here and you see here the value, or it also opens up here, and the value is roughly 0.27. So technically you could also simply say 0.3 here, and Matlab will update the location here. See, it moved. Whatever you put in here, if you put in here 2, it will again move and so on. But we said 0.3 is fine because it gives us a damping of 0.7. Okay, so we can hop back and answer that question. We need a controller of 0.3, a value of 0.3 to give us a damping of 0.7. Okay. So the question is now, do we trust ourselves or not? Well, it's always better to double check. And this is asked here. Finally, we want to close the loop in Matlab around our system. Now in the command line, not in scissor tools. In the command line Matlab, we can generate the closed loop using the so-called feedback command. The command assumes negative feedback. So all what we need is our system G and the controller R1. As your controller is located after the summation, you need to call the command like this. So what the feedback command is doing, it has X and Y in here. So you need two parameters, and the first parameter is in the feed forward part. If you consider your feedback loop here. And the second part is in the feedback loop here, right? Right, so this is what the feedback loop is doing, meaning that if we have our controller, remember we have it in the feed-forward part. This X here is R times G, so this means we need to put it in that way. There are sometimes strategies where you put your controller in the feedback path directly, and we are not going to do that. This is why we actually simply need a 1 here. Okay, so I'm going to hop over to Matlab again. So we're going to define our first controller with a value of 0.3, and then we're going to use, we're going to say our closed loop system. Actually, I figure it's hard to see. Let's do it this way. So we say R1 equals our controller, and then we say our closed loop is nothing but the feedback command. We take our system G, we will multiply it with our controller, and the actual feedback signal equals 1. And now we have the feedback, and we could simply say, let's see what the damping of that closed loop system is. Okay, why not? Did I put out GC1? Okay. Okay, and you see that we actually have a damping of 0.72, so we are roughly there, and we increased also our eigenfrequency to 2. Main point is we actually achieved the damping we actually desired. So if we want to check pole zeros, graphically, we can again call the pole zero map command, GC1, and then we can see, okay, poles are now, well, we don't see because we need to put on the grid. And now we should axis equal. If you don't do axis equal, it ends up like this. It's actually pretty not looking very nice, but now it does, right? So we are here now with a damping of 0.7, which is actually what we wanted to achieve. Okay. Yeah. If we want to do a step response now, we could remember step, for example, of our open loop was step G. Okay. This is how the step response of our open loop look like, so without controller. So we're simply going to hold on to that figure, and then we're going to plot the GC1 on it, and now we see how that has changed with proportional feedback. Now we are here, it's a little bit better damped, right, because we have this increased the damping. Still we have a lot of overshoot because of the zero, and we are the static gain has decreased, right, and this is what we know, that we are not able to achieve full steady state tracking with only proportional feedback. And actually the matter of fact is, with this gain what we actually have decreased our static gain in the closed loop. So this is definitely not what the pilot wants to see, because whenever he commands an input of 1, he only gets 20% of the output. Although the dynamics are nice, the static behavior is not yet that nice. Okay, so let's see what is next here. This is what we've done. We checked the poles of the closed loop. We called damping, okay, it has 0.7, and we compared the step responses. Okay, so we should write down some observations we had in terms of steady state behavior. Well, the overshoot is reduced, but still around 50%. And the steady state tracking, steady state error is not that good, right? So we are not happy with this one here. Okay, please for the exam write it down. Don't write smileys in the exam, but it should be clear. Okay. Again, although we have set a damping of 0.7 in a closed loop, clearly the overshoot is more than 5%. Why is that? This is simply because of the zero in the system, the zero mu. So what we could do is, again, we can compensate it with a pre-filter. So this would be an idea to solve with this, or you would also see when we add an integrator, we're going to add some laggy dynamics, so it's going to make things also better, that this zero does not take that much of an effect here. Okay, so far so good. What's next? Steady state accuracy. The first possibility, what you should know by now, is we can add an integrator to our controller, and actually that is pretty easy to do in the CISO tools, and this is what we should do. Describe in your own what happens to do the root locus when adding the integrator pole. Okay, so let's see how that works, right? So I'm here back with this CISO tool. we're going to open up our controller, which has a gain of 0.3, and now we want to add an integrator. Right? On paper, this would be quite some dramatic job to do. We need to recalculate everything, but we will see Matlab does it actually pretty efficient. So we can simply right-click in that field where it says Dynamics, and then we add an integrator. And you will see Matlab immediately updates everything what we have. Okay, our controller now is 0.3 times over S, right? So it's a pure integral control. And what you see is that we screwed up our system because now we have this additional pole here. It's still stable, however, we are not able to increase the damping here because the locus curve now go to the right. Interestingly, at this point, with this very low gain, we don't have any overshoot yet. But we have this a little bit of this strange behavior. Why we don't have the overshoot? Because we have a pole now here at minus 0.2. This very slow pole dominates our response, and this is what you see here. We are at a time scale of 25 seconds. This is definitely too slow for an aircraft. So you would need to increase the gain and speed up the system, and you immediately will see that the whole thing starts oscillating, and you don't want to sit in such an aircraft. So it's fast now, but it oscillates like hell. Okay, so our what we could write in here would be, for example, let's see where I am. Describe in your own way what happens to the root locus curves when adding an integrator. The damping, well, they go two curves. Curves go to infinity, meaning that we are not able to increase the damping anymore, and we get either slow response or a lot of oscillations. I mean, now you could do the mathematical interpretation, right? Why that happens, but at the end of the day, we have two poles which are there. We have this integrator pole, we have 1, 0, and basically these go to infinity because we have two more poles than zeros, and this is messing up our system. Okay, based on the root locus rules and having the damping increase of the conjugate complex pole pair in mind, which would be a better controller of using just a pure integral controller. Now you could argue with a lot of things we have learned. Well, you could say, well, just based on the root locus, I only want to have one curve going to infinity because then it would go right. Okay, I have three poles, 1, 0, to make that root locus curve go not to the right but to the left, sorry, go to the left. Simply we need a delta of 1, so we need three poles and 2 zeros, right? So how can we fix that? Well, we can simply fix this with a PI controller, because a PI controller will add another 0. It will solve our problem, right? So we can say, okay, we're going to use a controller which just has a certain gain, it has a 0, and it has an integrator, okay? Or you could say, well, I'm slow and I'm oscillating, so a 0 will speed up my system and it will damp the system, right? So this would be a different argument of adding a 0 in your controller, but with the same result, so to say. Okay, so that said, let's go back and try this out. So we are saying, okay, we don't like that behavior. So why not adding another dynamic, and we're going to add a 0, okay? And suddenly our controller looks like this. We have a 0, we have an integrator, and we have some gain, which is probably too high. Let's set it to 1 for a second, which is a classical PI controller. Matlab already updated our curve here, and we see this root locus curve now looks the following. This goes to the left. We have integral action, and here we are actually back to a similar behavior as before, without that integrator. So this is here the integrator zero part, which stabilizes our integrator, and this zero now takes, as before, takes care of our two poles to enable the to increase the stability. So the question is now where you place the poles, what gain do you choose? You can play around here. You could argue now, okay, where do I place the zero by the angle criterion and so on, but at the end of the day you have the gain and the zero already. I'm simply going to say we're going to place the zero at a value of -3. This gives us actually a nice for the angle criterion, and then we're going to increase simply to a damping back to 0.7. Oops, with a gain of too much. It's a little bit laggy, so it's not that nice. So let's do a value of 4 around something. I think that was the solution. So let's check when I click on it. Yeah, it says a damping of 0.71. Okay, so how do you get there? You see, now arguing with damping alone is a little bit hard. So you could also play around with poles and zeros here and look at your step response. And now, in my opinion, it looks fine. It's decently fast, right? It achieves the settling time is around 3 to 4 seconds. It's well damped, and it actually, looks pretty nice I think for the pilot behavior. So we don't have a lot of overshoot. This is why, because we have this very slow pole here, it actually makes sure that there are no overshoots happening because of the zeros. Okay, so we have a controller now, which is, let's do this on that side and get up our screen again. So we would have a controller which looks the following. R2 is nothing but, this is 1/3 S plus 1 over, we have an integrator, and we have a gain here, which we choose of 4. Okay, so finally go to the Matlab design. We're going to put in the controller, and we're going to see, okay, we can do that easily. So we're going to close that. And we're going to say our second controller is nothing but it's 4 over S times our 0, which was 1/3 times S plus 1. Okay, so this is our controller, and now we can again close the loop. Feedback, let's say G, our second closed loop we want to see is take our system and take the second controller. Okay, you see it's a little bit more involved now because we have some additional dynamics. And if we check the poles, we have one pole with which is at 0.57. Obviously, damping is 1, and we have the other two poles placed at 0.7. Okay, for example, we can do now step. We can do G. Let's do the open loop. We're going to check our first closed loop, and now we can do our second closed loop. So by that, it will all be plotted in a single file. Okay. The blue one is the open loop. A lot of oscillations. The orange one was the pure proportional feedback, not steady state accurate. And now we design this nice yellow controller, which actually gives us this pretty nice response. Now we would be actually done if the professor would not ask for more, right? So this is the last thing we're going to do. For the section, as a second option, we need to go back to the proportional controller, and now we're going to, instead of doing an integral, we still want to ensure the steady state accuracy by a pre-filter. Okay, so We should go to Matlab and see the static gain of our first closed loop, where we had this constant where we had proportional feedback. So GC1 was that, and now you can simply call DC gain. And this command gives you a static gain. It's 0.187. Okay, so let's do this one more time. It's up here. We can write that down. Okay, so 0.1878. Okay, if we correct for that, we know we're simply going to invert that GC, this gain here, and we get 5.3. Okay, remember we did that last time, the idea of inverting the closed loop gain to get steady state accuracy. Remember, the difference here is that this feed forward filter or pre-filter will not ensure steady state accuracy if you have disturbances. Okay. And the other thing, what we did last week was, if we want to correct for that 0, we can simply add a pre-filter. Okay, so we're going to add a pre-filter. Our 0 was at 0.7, so we're going to add a pole at 0.7 to shape the dynamics, and we have a gain of 5.3 here. Okay, that's basically it. Now we should do this whole thing in SysOtools, and let's see if we are able to get that done here. Okay, so I'm going to return to our original proportional feedback controller. We're going to delete everything here, and our feedback gain was 0.3. Okay, so this was the answer. We set the damping here, and we have this too much overshoot, and we want to fix that. So, as I said, this is only to add a pre-filter, and if you again take a look here, the pre-filter in that structure is F. So we're going to now work on this pre-filter F. So you can double-click to the left here. Again, changing the pre-filter is only a good idea if you don't consider the disturbances, right? If disturbances will not be affected by the pre-filter. One possibility would also be to kind of mix these two things, but yeah, you have endless possibilities here. We're going to say we make our system steady state accurate now with the pre-filter. Okay, we said, and now it's important to look here. We said we need a gain of 5.3. So let's start with that. And 5.3 gives us the step response to 1, right? So we solved that. However, we have this additional overshoot here. So we're going to add a real 0. And we're going to add, and now you have to, you cannot put in 0. Actually, you can put in minus 0.7 here. And now Matlab immediately does something. Sorry, not a 0, my mistake. We want to compensate the 0, obviously, with a pole. And we want to place that pole at 0.7 in our pre-filter. And now we actually have a nice response, right? Now we actually have compensated that 0 here in the pre-filter. The pre-filter now looks like this. It's just in time constant form, the 0 here, because otherwise you would need to add the 0.7 here as well. Matlab does that basically for you. We have it placed to minus 0.7, and we put the gain accordingly. And now we actually have a nice fast response, which is well damped. We have a damping of 0.7, everything's fine. So, and here probably one thing, if you don't do the canceling exactly, right? So you place the 0 at minus 7.5, it's also okay, right? You're basically adding some lag here to compensate for that 0. Here the lag is a little bit too much, so you basically have this over-damped behavior. But the point is, placing it around 0.7 is a good idea. We can do it exactly as we have perfect knowledge. However, we assume we know that the 0 is at 0.7. Maybe in reality, it is at 0.68 and you actually have some cancellation error, it's still going to be working fine, right? So it's not that tremendous. Okay, that's basically it for the scissor tool design. I'm going to simply close it. Technically, you could also save this whole thing. So we designed the pre-filter here. Well, you can do this, the same thing now in Matlab. You could say, okay, my pre-filter is 5.3 times, what did we have? Let's do it easy, 0.7 over S plus 0.7. Okay, this would be our pre-filter, and then you could say, okay, take our first closed loop, multiply it with our pre-filter, and for example, you take a look at the step response, and you get what we just have seen in scissor tools as well. So everything you can do with these GUIs, you can also do directly in the command line, which is usually a little bit computation-wise a little bit faster. Yeah, it depends on also what you sometimes like. Okay, so we did that. Yeah. And we also took a look at the step responses. Obviously, you could call damping, but I leave that for you if you wanna play around a little bit more. Okay, that's it for this A300 design. I hope you enjoyed it. I hope it gives you some insight where actually the whole thing is, how the whole thing, what we are doing in a lecture, is applied in practice, how you can do that. And this is actually what your job as a control engineer, your daily job is: designing controllers, working with models, analyzing it, and so on. And yeah, as I said, I think it was a good idea to now get that also on video, to have that how, on the one side, how can you move from the theory into actual practice, right? And the other thing, I hope it makes things a little bit clearer, because I know during the lecture we have, sometimes it's very theoretical, and what the application is actually not that hard, and it's actually everything what we do can be applied pretty easily. And I hope it gives you a little bit more insight and a little bit more understanding, and it helps you in understanding in preparation for the exam and so on. Okay, so far so good. I see you next week. As I said, this whole thing is because I'm not feeling that well, but it also is intended to embrace a little bit this flipped classroom idea. I'm not sure if any of my colleagues has tried it yet. The idea is that you work out this thing at home, for example, on paper, watch a video or whatever, and then the intention is in the next class, next week, we should discuss that and you come to me with questions. So please, when you went through that, I hope you write down your open questions, think about it, and then next week in the lecture, we're going to discuss that whole thing in a couple of minutes, and you can shoot me any questions which was not clear in here. And I think it should be a nice experience, and it should help you to understand everything we do in the course. Okay, hope you enjoyed it, and I'm going to talk to you next week, and stay safe. Bye-bye.